Okay, let's get started. Welcome to today's colloquium. And today our speaker is Dr. Mausumi Dikpati from HAO. Mausumi received her PhD from Physics Department of the Indian Institute of Science in Bangalore, India. And she came to NCAR in '96 and as an ASP postdoc fellow. Currently, she's Scientist 3 here at HAO. And Mausumi's primary research interests have been in the area of MHD of solar convection zone and Tachocline, with particular emphasis on solar dynamo theory and global HD and MHD instabilities of the Tachocline, and more recently on the application of data simulation to solar prediction problems using DART. And she was the first to build a physical based model on solar cycle prediction scheme. And I need to mention that one of our solar cycle projects was recognized in 2011 as the one of the top 100 discoveries by Discover magazine, which is very, very cool. And today she's going to discuss solar cycle simulations.
Thanks, Henry, for the introduction. So the outline of my talk is this. I'll first give some examples of observations of solar cycles and their impact on the Earth. Then I will describe a solar dynamo model that can simulate those many solar cycle features and can be calibrated for the Sun. One such calibrated model was applied for the prediction of solar cycle 24, and solar cycle 24 is the current cycle which is in its declining phase now. I will describe what we have learned from the validation or non-validation of cycle 24 forecasts. Observations also indicate longitude dependent solar cycle features, so I will describe how to go beyond 2D and include 3D Tachocline instabilities to explain those longitude dependent features, and also demonstrate their potential for predicting short time scale events which are called space weather. I will close by giving a future outlook. This is a magnetogram picture. Here the yellow-blue represent the bipolar active regions, the polarities of bipolar active regions. You can see that the leader spot has one particular polarity in one hemisphere and its opposite in the other hemisphere. This is generally called the Hell's polarity rule. Also, you can see the specific tilt. In one hemisphere it has one fashion, in the other hemisphere the opposite. This is the specific tilt is given by the Joy's law. If you look at their evolution, you can see the waxing and waning patterns as time progresses, and also you can see that the active regions appear in a particular latitude belt at 35-degree latitude, and then with the progress of time that latitude belt migrates towards the equator. The active regions decay and produce large scale diffuse fields that migrate towards the pole and cause polar reversal every 11 years. When this is plotted in a time latitude diagram, they look like this. This pattern looks like butterflies. So this is called the butterfly diagram. This part represents the evolution of active regions, whereas this poleward branch represents the poleward drift of the large scale diffuse fields and polar reversal every 11 years. Here I show another manifestation of solar cycle, the annual mean sunspot number as function of time. This is nearly sinusoidal pattern. However, the amplitude and frequency of the those cycles vary from cycle to cycle. The solar energetic particles and magnetic fields originate from solar activity, and these particles emanate from the Sun pervade through the interstellar space, interplanetary space, reach the Earth and strongly affect the terrestrial environment. On the one hand, you can these solar activity, the solar energetic particles cause beautiful aurora. On the other hand, it can cause damage of power grids and disrupting the power grid. It can cause blackouts. In August 14 of 2003, a massive CME, the coronal mass ejection, hit the Earth, disrupting the power grid, and that in the New York area, and that caused the blackout, which came out on the next day in the front page news. 50 millions lose power, city sweltered into a halt. This particular blackout I remember very well, because in this was the biggest blackout that happened in the United States in the past 20 years. And furthermore, at that time my husband used to work in New York IBM and used to stay in New York, and we were disconnected for a couple of days due to this blackout. Here is another solar cycle index, the F10.7 flux plotted in green, and in the bottom frame it is the atmospheric density variation. You can see very nice correlation between these two. So the variation in the atmospheric, this is the atmospheric density at 400 kilometer depth, and this variation in density can cause drag on the satellite. This is the depth where the satellites are placed, and the variation in the density can cause drag on the satellite, affecting their lifetime. Therefore, it is important to know the variation in the density to be able to place the satellites in the proper orbit. Solar cycle predictions were done over the past 60 years by using precursor techniques or empirical methods. And here I show about 200 predictions that were issued for cycle 24. That predictions vary in a wide range, starting from a very low cycle to very high cycle. So this doesn't help. We need to know the physics behind solar cycle, and so that we can eventually build the physics based scheme to predict them. Root of all solar activity is a magnetohydrodynamic dynamo. So what is a dynamo? A dynamo is a process by which the sun's magnetic field is maintained against its ohmic dissipation. The first solar dynamo model was developed by Parker in 1950s by including the sun's differential rotation and the helical turbulence. Parker's model can be best understood if we decompose the sun's vector magnetic field into its poloidal and toroidal component. Poloidal is in the plane of the board and toroidal is going perpendicular to the plane of the board. And we also know the sun rotates differentially, its equator rotates faster than its pole. So the differential rotation of the sun shears a pre-existing poloidal field to generate the toroidal fields. Toroidal fields are basically the spot producing fields. To close the dynamo loop, it is necessary to regenerate the poloidal fields. Parker proposed that the regeneration of poloidal fields is possible by displacing and twisting the flux tubes by helical turbulence. So a toroidal ring originally will look like this. When it undergoes the helical turbulence, it will form this wiggling pattern. And Parker also introduced the concept of magnetic buoyancy to explain their rise through the convection zone to the surface to produce spots. Identifying the sunspots as toroidal flux tubes risen to the surface and their equatorward propagation was explained by an equatorward propagating oscillatory dynamo wave solution obtained from Parker's model. The solar dynamo models have evolved over the past 60 years since the first model by Parker in 1950s. I am not going into details of those evolutions, but I am bringing in a widely accepted present day model, that is a Babcock-Lytton flux transport dynamo model. The first row, the 3 frames in the first row, I explained the mechanism involved in the Babcock-Lytton dynamo in this diagram. The first 3 frames represent the shearing of poloidal fields by the sun differential rotation to produce the 2 oppositely directed strong toroidal fields, which eventually rise to the surface by magnetic buoyancy and produce spots. Then this next row represents the spots decay and produce large scale poloidal fields. This is basically the Babcock-Lytton mechanism. These poloidal fields then get transported towards the pole by the sun's meridional circulation combination with supergranular diffusion, and a portion of that come down to the bottom, come in contact with the shear layer and get sheared by the sun's differential rotation to produce the new cycles toroidal fields of opposite sign. So you can see the sign change from this frame with respect to this frame in this frame. The Babcock-Lytton flux transport dynamo model's equation can be given by this in the kinematic regime. V is the mean magnetic field, V is the velocity field, eta is the turbulent magnetic diffusivity, and S is the Babcock-Lytton source term, which is equivalent to an alpha effect. The Babcock-Lytton process already I described in the previous slide. Here is the it arises due to the decay of active regions, tilted bipolar active regions, and that produce the large scale poloidal fields. These poloidal fields, this source term, when its longitude average, it produce a pattern like this. So basically it's like a Gaussian band migrating from 35° latitude to the equator, and then after 11 years it's changing sign. The turbulent diffusivity is 3 step. Near the surface is supergranular diffusion. In the bulk of the convection zone is the turbulent diffusivity, and below the base of the convection zone basically it's the radiative interior. So the diffusivity is very close to the molecular diffusivity, very low, it's very close to the molecular diffusivity. The flow fields are differential rotation and meridional circulation. Here is the differential rotation, which is parameterized from the helioseismic observation. You can see nearly a radial pattern, nearly latitudinal differential rotation in the main bulk of the convection zone. However, at the base, near the base of the convection zone, you see the latitudinal differential rotation change to radial differential rotation in a very thin layer. This layer is called Tachocline. I will bring in this again later in my talk. Meridional circulation included in this class of model is single celled in each hemisphere, and this is constructed from surface observation and mass conservation. Here is a solution from Babcock-Lytton flux transport dynamo model. The line contours represent the poloidal fields. They are generated by the decay of tilted bipolar active regions at the surface. Then they migrate towards the pole, cause polar reversal, and a portion come down to the bottom, come in contact with the shear layer there, and get sheared by the differential rotation to produce the strong toroidal field. Toroidal fields are presented here by the color shades which are going into the plane of the board. In order to compare it with observation, I bring in again the butterfly diagram that I showed. Yeah. Radial field. These radial fields. There is the boundary condition is potential field up to 2.5 solar radius, and then at 2.5 solar radius it becomes radial due to the solar wind. So how do you get the radial component of flow? It's a radial component of meridional flow. You are talking about meridional flow, right? Yeah, it's the because flow is radial here near the pole. In the high latitude, flow is radial, so it's dragging the field in the radial direction with it. Yes. Is basically the originated from the helical turbulence, because it is the Coriolis force that when the toroidal flux rises from the bottom of the convection zone to the surface, it undergoes the Coriolis force, and then that's why it gets tilted. And when it's tilted, that tilted bipolar active regions produce that net poloidal field. If it's not tilted, then you will get zero poloidal field. So basically origin is there. Since it's located near the surface, it's generally called from first proposed by Babcock and Lytton, so it's called the Babcock-Lytton source. So I show the model output to compare with observation. Model output is constructed taking the Tachocline toroidal fields and plotting the constant their amplitude in the time latitude diagram and surface radial field in the grayscale map. And you can see the good agreement with observation. The 11-year cycle period comes in this model from the meridional flow speed, and also the meridional flow speed governs the along with the turbulent diffusion, it governs the model's memory about its past magnetic field. So this model can be calibrated well for the sun, and this model was applied for predicting several solar cycle features. The prediction methodology is given here. The feeding the model by the surface poloidal fields derived from the spot area data, a strong cycle 24 was predicted. Cycle 24 started in the late 2009 and still ongoing. So this was the prediction for cycle 24. The basically the model works in this way. The latitudinal fields produced from the Babcock-Lytton effect comes down to the bottom by the meridional circulation conveyor belt, and from past 3 cycles the latitudinal fields get lined up in the conveyor belt and combine to produce the seed for the next cycle, and that's how the strong cycle 24 was predicted. Also a delayed onset of cycle 24 predicted from this scheme. Basically length of a cycle can be predicted from the knowledge of the speed and latitude extent of the meridional circulation conveyor belt, and length of a cycle is predicted, and hence the onset of the next cycle can be predicted. In this diagram, the simulated dynamo cycle period have been plotted as function of primary cell size of meridional circulation and as function of maximum flow speed. You can see that if the cell shorter the primary flow cell and faster the flow speed, the cycles will be shorter, and they are located in the bottom left corner. And if the latitude extent of the primary cell is longer and flow speed is slower, then that will give rise to longer cycles which are located in the top right. Observations indicate that during cycle 22 the primary cell was shorter, associated with a weak reverse cell at high latitude, but in cycle 23 it has a longer conveyor belt. The surface flow speed were the same in both cases, and therefore it gives rise to a slower return flow in the case of cycle 23. So longer extent of the primary cell and slower return flow places the cycle 23 here and cycle 22 here. Therefore from this diagram you can see why cycle 23 was 2.1 years longer than cycle 22. This was the work that was one of the top 100 discoveries that Hanley mentioned in 2011. Basically 3 dynamo based predictions were made: delayed onset of cycle 24, strong cycle 24, and south stronger than north. By now we know this has been validated. The cycle 24 has not been strong and south has been stronger than the north. So why cycle 24 has not been a strong cycle? I discussed 4 points regarding this. Phase shift between north and south cycles were not considered. Phase shifts can be caused by north-south asymmetries in dynamo ingredients such as Babcock-Lytton poloidal source, the meridional circulation, or appearance of inflow cells associated with active regions. This, however, during the prediction of cycle 24 in 2006, this phase shift was not considered in the prediction scheme. average and anomalous tilts of active regions were also not taken into account. No sophisticated data assimilation was used at that time. Only data was nudged for entire 12 cycles without frequent updates. And meridional circulation was used as single-celled in each hemisphere, which may not be the case. Observation indicate that indeed the meridional circulation speed and profile vary with time. So now I come back to discuss the first point. Unusually large phase shift of about 2.5 years between north and south cycle 24 was observed. Here is from the peak, north peak here from observation, and south peak here, about 2.5 years separated. Now this phase shift was not considered in Dikpati et al.'s prediction scheme. If the cycle north and south cycle would have superimposed, then here is the fictitious case. The north represented by green and south by blue, if they would have superimposed, then the total given by this red curve, you can see it would have been a strong cycle. But this has not been the case. Basically, there has been a large phase shift, therefore that strength has been smeared out. Then I come to the second point, poloidal source. Poloidal source was derived from amplitude of active region flux. However, if the tilts of some active regions are wrong, the flux from those will contribute negatively to form the seed of magnetic fields. For example, you see in this diagram, it is in the late declining phase of cycle 23, 2005 January. You see this spot, this is wrongly tilted. Correctly tilted spot is here, this is wrongly tilted. So if you derive poloidal fields from these two spots, they will look like this. The correctly tilted spot will produce this poloidal field, but wrongly tilted spot will produce this, and therefore that will contribute negatively and may reduce the seed of the magnetic field. So how to include the tilts in the poloidal source estimate? If it is derived completely from the amplitude of active regions, then you get this yellow curve. But tilt pattern from observation give this blue curve as a function of solar cycle. All these cases, these examples are being shown for cycle 21. So the combined effect of the amplitude and tilt will be this blue dash curve. So if we consider the tilt pattern with amplitude, then we get this poloidal field. Does this account for the actual poloidal source? This should be such that it could be able to explain the rate of change of polar field in cycle 20. This is the rate of change of polar field in cycle 21. So this source does not explain the rate of change of polar field. The additional, you need this additional factor plotted in red to explain, multiply with all the tilt and amplitude to explain the rate of change of polar field in that cycle. You can see this additional factor has a dip exactly near the sunspot maximum. It seems during the sunspot maximum, the surface poloidal fields are being sucked in. They are not going to the pole. They are not producing the polar fields. They are getting sucked in. So what could be the origin of this additional factor? Implementation of sophisticated data assimilation scheme requires the development of a dynamo dart system, which is in progress. I will not be describing this today. However, already OSIs have been performed for parameter reconstruction by assimilating data in a 2D Babcock-Lytton dynamo model. The next task is to build a 3D Babcock-Lytton dynamo model that can operate in a data assimilative mode, and this is already ongoing. The biggest challenge is the meridional circulation. Is meridional circulation a single or multiple celled? Single cell produces the solar cycle features well, but if it's two cells in depth, then it does not. And recent observation indicate that there are two cells in depth. However many cells are there, the flux transport dynamo models need an equatorward return flow at the base of the convection zone to have the toroidal fields held there, amplified and transported in the correct direction. So, so far I mentioned how to simulate the longitude average solar cycle features and how it was applied for solar cycle 24 prediction, and from what we have learned from the validation and non-validation, as well as how to refine for further cycle prediction. Now I want to bring the longitude dependent features. Here you see in this two column the longitude in this direction and latitude going from 0 to 60 degree north and south, and each strip represents one rotation. Active longitudes are active longitudes, you can see they persistently appear in a longitude or two longitudes separated by approximately 180 degree. These are called active longitudes. They rotate, if they are strong, they rotate rigidly, but also faster and slower rotations have been observed. They can persist for 15 to 20 solar rotations, and modulations over several months to few years have also been observed in their amplitude. Global organization of persistent longitude dependent features as well as the oscillating signals, oscillating magnetic signals, say that they are originated perhaps in the deep interior somewhere at the base of the convection zone or in the Tachocline region. Here I show an observation of Tachocline from helioseismic inversion. These are the latitudinal differential rotation in the main bulk of the convection zone, and then you see the radial differential rotation. This radial differential rotation, this strong shear layer is called the Tachocline, and dash line is the base of the convection zone. So anything above the dash line is the overshoot part, this is the overshoot Tachocline, and below it is the radiative Tachocline. Extensive studies indicate that Tachocline, from the Tachocline dynamics, that in 2D, quasi 3D and 3D, that there are instabilities, and that instabilities produce pattern with large scale longitudinal modes with low longitudinal wave number, as well as periodic oscillations of few years to few months. So I want to describe Tachocline instabilities in order to show you how to explain the longitude dependent features. Here is a shallow or quasi 3D shallow water model of the Tachocline. Basically, Tachocline fluid is in a thin shell whose bottom boundary is rigid and top boundary can deform. Horizontal flow and fields in this shell are independent of radius, but vertical flow and fields can be function of radius, linear function of radius. This is in magnetohydrostatic force balance, and horizontal divergence of magnetic flux in a radial column is 0. I am not showing, describing in details the shallow water equations, but basically these are the equation of motion and mass continuity equation you can readily get in Pedlaksky's book, and there is MHD analog. So this is magnetic induction equation and flux continuity equation. Shallow water model can be solved, numerically solved, and there is a parameter, dimensionless parameter, that I need to describe. This is called the effective gravity parameter. This is related to the actual gravity at the Tachocline depth, the subadiabaticity of the Tachocline fluid, the thickness, the scale height, the radius of the Tachocline, and the core rotation rate. And if we compute these numbers, the effective gravity comes out to be small, 10 to the minus 1 in the overshoot Tachocline, but large, 100 or 1000 in the radiative Tachocline. The possible modes that can occur due to this instability are these: m equal to 0, m equal to 1, m equal to 2. Actually up to m equal to 7 modes can occur, but these are the main modes. M equal to 0 looks like this. The height increases poleward, toroidal ring shrinks, and fluid in the ring spins up. In the case of m equal to 1, height or thickness of the tachocline gets redistributed, but there is no net rise, and toroidal ring tips but remains of same circumference. Fluid does not spin up in this case. In m equal to 2, height again gets redistributed, but no net poleward rise, and toroidal ring deforms, and fluid inside the ring does not spin up. Here is a solution from MHD shallow water model in a latitude longitude plan form. So, here the color represents the height or thickness of the tachocline, and the arrow vectors the toroidal band. Red represents the height and blue the depression. So, you can see the tachocline toroidal band is deformed due to the instability in such a way that portion of the band falls in the swelling region and portion in the depression region. The portion of the toroidal bands starts entering into the convection zone first, that is coinciding with the swelling region, and that is the place where that is the longitude where the spots will form. With this concept, I explain the evolution of active longitudes. Consider a toroidal band of 20 kilogauss peak field and compute all plausible shallow water unstable modes. Basically, there are not too many. There are m equal to 1 symmetric mode, antisymmetric mode, and m equal to 2 antisymmetric mode. And then construct a total toroidal band. That means adding the perturbations according to their the amplitude decided from their growth rate, and add a linear superposition of all those perturbations, add to the unperturbed state and construct the toroidal band configuration. And so choose the phase, initial phase of this phase have they in the rotating frame they propagate in a faster or slower motion, slower speed. So, set their initial phase in such a way that the toroidal band fall into the swelling region to explain a certain synoptic pattern that has these active longitudes. This is in 1997 April. And after then don't touch, allow them, allow those modes to propagate according to their own phase speeds. So, after 6 rotation, the toroidal configuration will obviously change, and this is the new configuration, and after 6 rotation this is the synoptic map with new active longitudes. And see, again the swelling regions, that is the red regions, coincide with the band that you can match with the active longitudes. After additional 9 rotation, you can again allow the phase to propagate with their own phase speeds and obtain the new configuration of the toroidal field. After additional 9 rotation, you can still match the active longitudes from these swelling regions to the synoptic map where you see the observed active longitudes. But now we have evolved about 15 rotation and we start missing also. See, this active longitude, this active region does not coincide with any swelling, rather it is in the depression region. So, this is done through a linear study, taking the linear combination of all perturbations, and still we can explain up to a certain time, but this is about 14 months from 1997 April to 1998 June. So, it is 14 months we can explain, but we start missing. Therefore, we can clearly see the nonlinear interactions are coming into picture. Here is a solution from nonlinear evolution of shallow water instability. Again the color map represent the thickness of the tachocline. You can see the swelling and depression, and the vectors represent the global flow. It is clockwise in swelling and anti-clockwise in depression in the northern hemisphere. And flow is nearly geostrophic if it is hydrodynamic or weakly magnetized tachocline. This solution has another interesting feature, that the interaction between reference state kinetic and reference state kinetic energy and perturbation kinetic energy is oscillatory, with an oscillation period of about 6 to 18 months. So this is in non-dimensional time scale, and about 35 represents the 6 months. These oscillations are essentially related to the oscillatory interaction between Rossby waves and differential rotation, and these periodicities organize the space weather that influences the Earth. And you can see the burst of activities. This is a daily hemispheric sunspot numbers from observation. The daily flare rate from observation, dash lines represent the year. So dash lines have been plotted in 1 year interval, and you can see the burst of activities with an approximately 1 year periodicity. Burst of flare activities also with an approximately 1 year periodicities. So from these Tachocline instabilities and oscillations of magnetic signals, we may be able to predict this. That is what I said, that I will demonstrate how to simulate the longitude dependent features and short time scale space weather type events. Predicting solar cycle amplitude and duration and timing are very valuable. However, imagine one scientist can get the opportunity to study about 2 or 3 solar cycles. There are features within a solar cycle and which are short time scale features that can more frequently affect the Earth. And current forecasts are done in the way that the predictions are made after the CME has been observed, giving little time to prepare to protect the terrestrial system from the damage. So it would be very valuable to forecast space weather events enough ahead of time. Imagine that East Coast storm that occurred in January, last week of January, and we had an international conference, and many participants from the United States were traveling from the East Coast. And 5 days ahead of the trip, we got alert from the United Airlines that we need to reschedule the trip because that day there will be this big snowstorm and the flights will not leave. So 5 days ahead means 5 rotations of the Earth. Similarly, if we can predict 5 rotations of the Sun ahead, that will be about 5 months, 4 to 5 months ahead. That's a great thing to do. So why not close the stable door before the horse bolted? So now I want to review what I have talked so far. I gave examples of observations of solar cycle, and I showed few examples how it can impact the Earth. I described a solar dynamo model that can simulate longitude average as well as longitude average features and can be calibrated for the Sun. Observations also indicate longitude dependent solar cycle features, and I also explained what we have learned from the validation or non-validation of solar cycle 24 forecasts and how to refine for future predictions. Observations indicate longitude dependent solar cycle features, and I explained how to go beyond 2D and explain the longitude dependent solar cycle features from quasi 3D Tachocline instabilities and demonstrated its potential to be able to predict the space weather type events. And now I want to talk about future outlook. So we need to couple the Tachocline instabilities into a 3D Babcock-Lytton dynamo model. We need to utilize the observational data and operate the model in data assimilation mode, and then we can predict decadal time scale as well as short time scale phenomena within a solar cycle, that is space weather and space climate both together. And thank you for all who have come to listen to my talk, and special thanks to these people for helping me in the dry run. Thanks.
questions?
Okay, I have two questions. One, what is the energy source for shallow water instability?
If it's hydrodynamic, this is the kinetic energy of differential rotation, and potential energy also, because we have the height, thickness of the Tachocline. And when magnetic field is introduced, then depending on whether the magnetic field is strong or weak, it could be magnetically dominated or still hydrodynamically dominated. If it's weak magnetic field, then it still shows hydrodynamically dominated features. And if it's strong magnetic field, like if you think of 100 kilogauss toroidal band, that 50 to 100 kilogauss toroidal band you may need for producing spots in the correct latitude. If you think of that, then it's magnetically dominated. And then in that case, you will see the features which are magnetostropic.
Okay, and the second question, when you said that oscillations is caused by interaction of Rossby waves and differential rotation. So this is a numerical results, or this is your interpretation, or you use some dispersion relations for Rossby waves, and is it analytical result or what?
It's the numerical result of reference state kinetic energy, that is differential rotation, and perturbation kinetic energy. So then I interpret in this way that suppose when there was nothing, there was still Rossby waves, and then you introduce the differential rotation. So the differential rotation, you introduce a differential rotation which is suppose a stable differential rotation. Then it will extract the energy from Rossby waves, and eventually it will be unstable. So when it becomes unstable, then it will energy can be extracted from unstable modes. So the, first Rossby waves feed the differential rotation, and it gets unstable, and then it gives the energy to the Rossby waves, and when it loses its energy to Rossby waves, it becomes stable again, and then Rossby. So the interaction that I showed here, see, they are out of phase. So when this is maximum energy is being extracted to go to the perturbation, and then when its minimum is stable, then it's again gaining the energy from perturbation to become unstable. So that oscillation is going on. So that I interpret as the interaction between differential rotation and Rossby waves.
These Rossby waves are two-dimensional or three-dimensional?
These are three-dimensional. Shallow water is a quasi 3D model. Yeah.
Well, first of all, I think it's very sobering to see how wrong the sun can be. I mean, that active region there with the wrong polarity, that's, yeah. But I was a little confused about how you accounted for that. Yeah. Oh, yes, that one. But in the next slide, you're showing how you account for that in your source.
This one?
In the next slide, you're showing how you account for wrong polarity in the sources.
Oh, here?
The green line, yeah, that's
green line is the tilt pattern. This is from observation derived by you can get the formula in Kosovicev-Steinflow and Kosovicev, or Kosovicev and Steinflow 2012 paper. Also very recently by Yiming Wang, you can get this tilt pattern. Actually he computed as function of latitude. If there the active regions are appearing at 35-degree latitude, the tilt is maximum, and it's the statistical. And then when they are going to lower and lower latitude, that average tilt is decreasing. And so I converted the latitude in time as function of cycle. So this green pattern is that.
But
and so I just simply multiplied the amplitude obtained from the active region amplitudes and the tilt of the active regions. I just multiplied, and then I get this this curve, which does not account for the polar field change.
But it looks like you multiplied the yellow curve and the green curve.
Yes.
And the green one is not measured. That's just a statistical.
No, that's measured. It's measured. It's measured from white light pictures. White light and yeah, magnetogram is measured from.
But it's not for this particular cycle and for these particular.
Oh, this
years.
I put in a particular cycle. I have computed it for 21, 22, and 23.
Okay.
And my main point here is to show this this curve, this red curve. This is quite universal for all cycles, and that's why I said that you need this curve to multiply additionally with the amplitude and tilt to obtain the correct polar field change, rate of change of polar field. And what could be the origin of this additional factor?
Mausumi, would it be fair to say that at this moment you don't know what the initial factor is? You've just recently discovered this relationship.
Yeah. This is still, this work is still in preparation. I recently discovered this additional factor. I still don't know. Only one idea is coming into my mind, that it could be the inflow cells due to active regions, because inflow cells are the ones that can suck in the poloidal fields from going to the pole.
If you could also go to your nonlinear shallow water simulations, you might talk just a bit more about typically what is the spectrum in longitudinal wave number that you excite. My understanding of the model is you can get in principle all wave numbers, but in fact it's dominated by wave numbers 1
yes,
and 2.
I have done this simulation in 2 ways. Just by initializing at t equal to 0, taking the configuration of m equal to 1 mode from linear study with random amplitude, and then it develops its spectrum in the higher longitudinal wave numbers also, not too many here, m equal to 1, 2, and 3. And here the differential rotation is such that it's primarily dominated by 1. And I have also done another case, another experiment that I initialize randomly, so that can have all smaller wave numbers, but eventually during the evaluation they land up to the large scale, low longitudinal wave numbers.
And to what maximum wave number do you go in the simulations?
In pure hydrodynamic case, it's 3. Maximum is m equal to 3, but in the if I include magnetic field, then I can go up to m. Oh, you are asking
what's the full spectrum?
The initial. Oh, full spectrum.
That is when you do a full nonlinear calculation.
Full spectrum, I have gone up to m equal to 40.
40. Okay.
I was kind of interested in the prospects for initializing the dynamo model for predictions. And I'm assuming you're initializing with some kind of observations of something, right? But the question is, do you have enough observations, especially the vertical structure of the Tachocline, to do a initialized prediction, or what kind of observations are you going to use to do that?
You mean for the short time scale events, for predictions? Tachocline is well resolved. Tachocline is from by helioseismic observation. Tachocline is well resolved. The uncertainty is in the higher latitude. Beyond 60 degree, exactly what is happening we do not know. And bigger issue is the meridional circulation, because we have only observation in the upper half of the convection zone, and also that is up to 60 degrees, so polar region we do not know. And therefore it is true that in order to obtain the correct profile of the ingredient, we need, along with observation, the data assimilation. I did not discuss today the data assimilation work. There I am studying whether from observation basically I have so far done only OSI, the observation system simulation experiment, so it's synthetic data, but when that will be converted into the real data, it can talk about, by assimilating the surface data, it can talk about what profile and speed it can have in order to match the surface observations. So that will help.
So a question about the active longitude. So we've seen in irradiance data that the active longitude shows up best doing near and through solar minimum. It gets more confusing doing solar maximum, but it shows up every solar cycle for the last four decades. The modes that you were presenting that could explain the active longitudes, do they have a solar cycle dependency, and can they be repeat or be stable over many solar cycles?
Let me understand if I understood your question. You are asking about the active longitudes that are seen in the synoptic map and active longitude pattern you see in the solar irradiance. They have slight differences, right? That is what you are talking?
No, what we see is you can clearly see the active longitudes near and through solar minimum. It gets a little bit more confusing at solar maximum because there's so many other activities. And the question, I guess, is do the modes that you're modeling,
yes,
do they
I got,
change with
yes,
solar cycle, or are they
yes,
there throughout the solar cycle?
throughout the solar cycle, and in order to explain throughout the solar cycle, yes, minima is the near the minima and the early rising phase, you see the clearest pattern, and during that time you can explain the active longitudes. I'm just guessing, I haven't done the nonlinear evolution of active longitudes. As I showed, that was from linear study. So I am just guessing what could happen. In the linear study, it says that if you place, if your toroidal band, dynamo generated toroidal band at high latitude, like mid latitude during the minimum in the rising phase, and your major mode is m equal to 1. So you can see the active longitude, and then the longitudinal wave number increases as you place the band at lower and lower latitude, which will happen as function of solar cycle, and up to m equal to 7 can be generated when you go near the maxima and go past the maxima. And if those many wave numbers are generated, there will be nonlinear interaction also. So you will see those more complicated patterns.
You mentioned the breaking of Rossby wave. On Earth atmosphere, you can use some diagnostics like a PV gradient or something to look as a diagnostic tool to look at that. Is it possible to do the same thing for solar?
Yeah. That's why I brought this Rossby waves thing to explain this burst of the interaction between Rossby waves and differential rotation, to explain this burst of activities with 1 year time scale.
But it is possible in
Yeah.
your model to do diagnostic studies
Yeah,
to look at
yeah.
Okay, to confirm whether you really have an instability.
Yeah.
Hi, so in your model it looks like you find that it's very sensitive to sort of small surface effects. Sunspots that are oriented the wrong way, the amplitude and the frequency are sensitive to things like the sunspot that's oriented the wrong way, maybe it's some number of them, and changes in the meridional flow. So then that leads to the question, why is the amplitude and the frequency as stable as it is? Why we wouldn't see 2-year or 20-year cycles, or a wide range of amplitudes if these little things are so important?
Apparently it looks like randomly some active longitude active regions appear with wrong tilt and contributed wrongly, but that's why I showed this. That's why I showed this, that there is a systematic tilt pattern, statistical effect, So, and these systematic tilt patterns and amplitude of active regions combined do not produce the polar field changes. You need this another systematic factor, and this is not, I presented only for solar cycle 21, this is valid for cycle 22 and 23. And so there is a systematic pattern, right? There is even though there are these small scale effects of appearance of wrongly tilted active regions at certain phase of solar cycle, and there are randomness, but there is also a systematic pattern behind that randomness, and that is coming from this large scale organization. The small scale pattern organized into the large scale, and that's producing that. So Regner is going to ask another very difficult question. Yes, tell me.
We're back at this plot here. Why don't you just, for each active region, when you're summing up the contribution from each active region, just project it onto the whatever optimal tilt it is, so you get the actual contribution to the source function here. I don't believe that the green curve is what is actually relevant for this particular cycle. I mean, it can be a straight line. It has to fluctuate.
But it's from published paper. It's the statistic. Yeah. In this is what I am showing, what could have improved the 2D situation, and what you are saying that needs 3D, and that I propose that we need to eventually build the 3D, and then the bottom I bring in that last slide where I had that feature. Yes, so this 3D Tachocline flow and 3D features coming from the large scale organization of longitudinal modes, those things that will govern the location of active longitudes, and then they will erupt to the surface to produce the 3D Babcock-Lytton source. So you can simulate them directly if you go to 3D. What I was showing you, the average statistical effect, that the best you can do when you use 2D. What? Yes, yes.
Yeah. So instead of just measuring the amplitude, also measure the tilt, so that you can project it onto whatever tilt they're supposed to have, and weight it by that. And then you get the proper source for your model. You don't need to treat in 3D. You don't need to change anything. It's just about how you measure the source that you're putting into your model. Your data is simulation.
It's not so easy. Do it. If you think, do it. Measure the active regions, measure the tilt, measure its amplitude, and derive the poloidal source, and see whether that can explain your polar field pattern. Just do it, and you will then realize.
Sounds like a good future project to work on, I guess. Okay, let's thank our speaker again. Thank you very much.